Hey guys, so what I want to do is make a little video for you on this concept of torque. So when we study linear motion, one of the first things we did is we studied the kinematics of linear motion, how we can describe the motion in terms of velocity, acceleration, and displacement. And we did the same thing with rotational motion. So we talked about kind of how we define displacement and radians per second, how we define velocity and acceleration. Then we talked about the kinematics involved with rotational motion, how essentially those equations are the same as the linear kinematic equations, just kind of with different variables. There's a lot of analogies between rotational and linear motion. And so the next thing that we talked about in linear motion was, okay, well, what causes acceleration? How can we change the linear motion of an object? And we said that it was by applying net force. Now we can also change the rotational motion of an object, but instead of simply applying a force, what we do is we apply what's called a torque. So I wanted to explain to you guys what torque was and how we calculate it, and then kind of set you up to do some problems. So torque. You imagine a door, so I try to draw kind of a door here. Here's the handle, there's the hinge. So we have a door and we apply a force to this door. Now usually we would apply it at the handle, and notice that this handle is pretty far away from the hinge. So we would have kind of this distance right here, and I'm going to call, let me fix that, okay. I'm going to call this distance R. Okay, so let's call this distance R. Okay, and then I'm going to apply a force to this as well. So I'm going to apply a force. Let's see, where should I apply this force at? Say I'll apply this force at the handle. That's what we usually do. So we'll apply a force at the handle. Some force, let's call this F. Okay, so I'm not sure what happened there here. There's R, and then we have some force F. And so we will be applying a force to this door. Usually we would be applying this force straight perpendicular to the door. In this case, just to kind of show you some examples, we're going to apply at an angle, which isn't ideal. And the idea is that we will, in doing this, we're going to change this rotational motion of the door. Now you can imagine that we could also apply a force. I'm just going to draw this in maybe right here. Okay, let's call this F2. So maybe I could apply a force at F2, and you kind of think to yourself, well, which one would be more effective, at opening this door? Is it going to be let's call this F1. Is it going to be F1 or is it going to be F2? And we look at this and we say, well, of course it's going to be F1. But what we want to do is we want to explain why. Why is it that F1 would be more effective than F2 and pushing on the middle of the door and opening it? So with F2, we have this radius, this different radius right here. So let's call that R2, and maybe this will be R1. Okay. So when we think about changing the rotational motion of an object, we realize that we have to apply a force to it, but the other thing that matters is how far away from this pivot point. So we have a pivot point right here. In this case, it's the hinge. So how far away from the axis of rotation or the pivot point we apply the force matters too. And this all gets tied together in this concept of torque. So with torque, we symbolize torque. We like Greek symbols with rotation. So we have this tau. Okay, so torque is what we'll use for that. So torque is going to be equal to the magnitude of the force that we apply. And I'm going to use that symbol right there, multiplied by the radius. Now this, let's call that radius, and this will be the force. Okay, this will be in newtons, and actually I'm going to change this up on you guys. So rather than calling that the radius, let's call it something else. Let's call this the distance from the pivot. I like that better. Distance from pivot. Okay, and that's going to be in meters. All right, so we have that, and you would think it would be so nice if all we had to do is multiply the magnitude of the force times the magnitude of the distance from the pivot. Unfortunately, it doesn't work that way, because you can imagine that if we apply a force to this door, if we were to apply a force, like this, it would, even though we're applying a force, even though it's far away from the pivot, it would have no effect whatsoever on the rotation of the object. Okay, so it's not just the magnitude of the force, nor is it just the magnitude of the force and the distance from the pivot, but the relative direction between these two matters as well. And so when we look at these forces and we think about, okay, well, what part of this force is actually causing this change in rotation, and looking at the components of the force, we zoom in on the perpendicular component of the force. Okay, so this component of the force that's perpendicular to this line that connects the pivot to where the force is being applied. So this is going to be kind of the important part right here, this perpendicular component. And you can kind of see if there's like an angle, let's call that phi. So if there's this angle phi between this line that lies along this, goes from the pivot to where the force is applied, so this would be this horizontal line in this case, and there's an angle phi between that and the perpendicular, or between that and the force, then this over here would be F times the sine of phi. Okay, so we would just want this component of it. And so what we do, and with this little x thing here, this x represents what's called the cross product. Okay, so if you guys are taking linear algebra, you probably have come across these before, maybe in pre-calc. But there's the idea of the cross product. So really the way we can write this is we can say that this torque is equal to the magnitude of the force times the magnitude of the distance from the pivot times sine, times the sine of just call it theta. Okay, you call it really whatever letter you want. Okay, so this is the expression for torque. Okay, so you can imagine that, say we have this bar. Actually, I'm gonna really get freaky here. Let's go ahead and make this so that now. Let's make this so that, let's twist it a little bit. Let's see. Let me twist it. Yep, I'll rotate it. All right, having some technical difficulties here. Just draw it in then. And all right, so let's say that we have this bar, and now it's at an angle, and we'll apply a force straight down right here, and say our pivot's right there. And we have, this R right there, okay? And say that we know that the angle between these two is, 40 degrees. Okay, so that's what that angle is. This theta here that we want is going to essentially be, if you run along this line right there, okay, the theta that you want is this theta between between the line that connects the pivot to the force and where the force is being applied itself. So you can kind of see how this force kind of has a component goes out this way and a component that goes over this way, and it would be the sine. Okay, I'm going to use a different color here. Okay, so we have two components. We have this component. Oops. All right, so we have this component, and we have this component. Okay, and we're going to zoom in on that component and say that that component's going to be F times the sine of 40 degrees. Okay, so even if this is at an angle, if you know the angle between this line that connects the pivot and the location where the force is being applied, you can still use this equation, and you would just plug that angle in for the theta. Okay, so that's pretty much, that's the calculation of theta. And once again, we have this idea of positives and negatives. So if we look at the sign of torque, okay, so sign that torque has, the sign of the torque. This might require you guys to use your pens or pencils and kind of set up a model so you can see this. But if torque is in the counterclockwise direction. So in other words, if when you apply the torque to an object, it would change its motion, its rotation in the counterclockwise direction, then we say that that's a positive torque. And if the torque is in the clockwise direction, we say it's negative. Okay, so that's just staying with our convention that we had before as far as the signs of these various quantities, like the angular acceleration, the angular velocity. So you can imagine that we have our bar here again. Just pretend like it's uniform, and say our pivot's right there. Okay, so there's our pivot. To just make things easier, say I'll have one force that's going up this way. I have one force that's also going up maybe this way. Okay, so call this F1, call this F2. All right, if we look at that, and if our pivot is right there in the middle, then you can kind of see that if we focus on just F1, so we're just going to focus right here on F1, if that was the only force acting on it, it would cause it to start rotating or change its rotation in that direction, the counterclockwise direction. So I would say that that would cause a positive torque. Okay. Now, at the same token, this is also going up, so you can't go by up or down, whether the force is up or down. You got to go by clockwise, counterclockwise, which requires you to know where the pivot is. So the pivot's right here. This would create a torque that would cause it to rotate like that in the clockwise direction. Okay, so you can imagine there's your pivot. This force is applied to it. It would change its rotation in the clockwise direction. And so this one would create a negative torque. Okay, so torque has signs just like the angular acceleration, just like the angular velocity does, and you're going to have to pay attention to them. Okay. All right, and that's pretty much all I have.